Okay, we're going to give a presentation here. I'm learning how to do this. This is about my third time doing this on Screencastify. So third time's a charm is what I hear. Okay, hopefully I can get through this within 5 minutes. And I think I will, since this is my third time to practice. So we have a chart on page 340. If you have that page open, you will need to have that open in the future to do problems. You are familiar with the alkanes. Here's a list of the alkanes, methane through decane. Here are the formulas. You know what those formulas stand for. Like C5 is pentane. Something you do not know much about is this number here. It's called heat of combustion. That's in kilojoules per gram. That means for every 1 gram, it gives this amount of kilojoules. So if we're talking about methane, for every 1 gram, you get 55.6 kilojoules. Now, you should know what a kilojoule is because we did calculations when we burned kerosene and methanol and a lot of the different fuels in lab. This here we'll talk a lot more about in the future. This is not in values of grams, but moles, which is based upon our balanced reaction. We'll get to both of those in the future. So here's our simple reaction. If you take natural gas, burn it with oxygen, which you guys did, that was your best heat source, you get off two products, CO2 and H2O. So there's your balanced equation. On balanced equations, we want to show heat produced. Heat's going to be on the product side because it's produced. So what we're going to do is we're going to look at this 890. We have to use the 890 because it's within a reaction. So then when we put in our reaction for methane, one of this burning, you get 890 kilojoules. So you're going to have a couple of those to write out. Real simple. You write out your products, CO2 and H2O, balance it, and then look up what it would be in kilojoules per mole and write that to the right side of the reaction because you're getting it produced. This is just a simple energy diagram. It says you put energy in to separate those molecules, and when you put them together again, you get energy out. We'll go to that, look at that in the future. So here's a problem. Okay, what we're going to do is look at this problem. It says if you got 40 grams, that means if we take and use up 40 grams and burn it, and we burn methane gas, how much energy is given off? So this is per gram, and so what we're going to do is we're going to look at this number because it's in kilojoules per gram. In your book, it's not, but you got to realize that third column should be labeled kilojoules per gram if it's not. Okay, so there's our number of kilojoules per gram. This is how many grams we're burning. So all we have to do is multiply the grams by the kilojoules. Since it's per 1 gram, the grams cancel, and it tells us the total energy given off, 2,224. Those are really simple. You just multiply it out, gets rid of your grams, it tells you how much energy you give off. Second type of problem is more difficult. You get students who usually have more difficult time with this one. This one is how many grams of propane will produce 220 kilojoules. So now it's asking how many grams do you need to produce so much energy, which is just the reverse of what we just did. So we're going to find propane. It's 50, nice round number, 50 kilojoules per gram. So there's our 50. We are going to want to know how many grams it would take to get to 20 kilojoules. Well, for every 1 gram, you get 50. For every 2 grams, you get 100. For every 3 grams, you get 150. You kind of see how that works. So then when we set up our problem, we're going to have 220 kilojoules. Put that number in front. Now what happens most times, students will put 50 over 1, but the units won't cancel. So we reverse this. And so we put the 50 kilojoules on bottom so it cancels out. And then we'll end up with grams on top. And if it doesn't make